All right, so maybe just say a little bit about the schedule. So we have one session now that's something between an hour and 75 minutes. There's reception afterwards, but the start is, kind of flexible. So probably we'll go closer to 4:15 than 4. And then we start tomorrow at 9 a.m. And there's coffee and breakfast at 8:30. Great. So our first speaker will be Erez Petrank, who will talk about memory reclamation for concurrent data structures.
Yeah, thanks. I will speak about, initially I thought of talking about a specific thing and getting into the technical details to the death, but I realized that there are both experts and some people who are new to this area, so I'm going to talk more high level and just mention results and talk a bit about technical issues. It all started about 25 years ago and with kind of 2-3 papers. And I brought, a couple of years ago, they got the Dijkstra Award for the initial 2 papers. I found pictures in my photo album of Maged Michael and Maurice Earlehy. There are maybe 3-4 more authors who won the Dijkstra Award for that initial paper. And so 25 years ago, they kind of started to discuss how to reclaim memory for concurrent data structures. And they gave 2 solutions that I will show that have not been the best solutions. There are some problems with these solutions. And it took about 10 years until researchers started to suggest improvements to these algorithms. And then there was like a flood of papers, I think. By now, there may be 100 papers about this. There are a couple of PhDs or more. So there are lots of papers. I will highlight one of these continuation paper that I think is more, diverts more from the original methods. So this is Nachshon Cohen, who he said, we do optimistic methods almost everywhere in hardware and in concurrency, in software, but we never do it in Memory Manager. So if you run garbage collection for Java, it will never be, it's always conservative. No one touches anything that has been reclaimed. And Nachshon said in this specific domain, maybe we can have some optimistic methods that will work. And he tried it and it worked. I will tell you a bit about it. And then Maurice joined us for a subsequent work, and also Gali Sheffi, who's a student. And we did subsequent work, and it was eventually accepted to disk. But before that, it was rejected from a conference with reviewers saying, you have to give us more and more. And Gali was really upset. This is Gali upset. And she said, we cannot do all this. How can they? So they want efficiency, and they want low memory overhead, and they wanted a lot of things. And she said, this cannot be done. And I said to her, why don't you show theoretically that cannot be done? And she did it. So now we know that you cannot have the best memory reclamation for concurrent data structures. That explains perhaps why we have 100 papers instead of 1, finishing this job. And I think it's interesting to look at this impossibility just to understand what you have to duck, right, to overpass in order to get maybe the best solution. So these are the 3 things I'm going to talk about very shortly. We'll try to do about 10 minutes each or a bit more. We'll see. And the slides are due to Gali. She has beautiful slides. So the running example is a linked list that represents a set. In the linked list, everything is sorted. So in this set, you have 23, 18, and 7. And you can insert a key, delete a key, and check if a key is in the set. These are the things you can do. And you have to agree with me that I must reuse memory. Otherwise, all of this is not interesting. But if you don't reuse memory, I do inserts, deletes, and the deletes, just accumulate space until, if your memory is finite, it's exhausted, and then you cannot do any more allocations, so you cannot do any more inserts, and you cannot continue to execute. So we need to reuse memory. How do we reuse memory? So if I deleted 18 from the list, and you see I disconnected it, now I can, use this space, right? Normally I can put it in some reclamation box, and if I now need to allocate some space for 43, I can take this thing, put 43 in it, and, make the arrangements in the pointers to add it to the linked list. So I want to have something like this. If you look at the sequential setting, this is how you do it. It's trivial. There's nothing to talk about. In the concurrent setting, this doesn't work so easily. So let's go through this. Suppose I want to be able to delete and reclaim. Now I have two threads. One of them wants to delete 15. The other one wants to check if 43 is in the list. Now, 43 is going to be in the list all the time, so you have to say yes. He cannot not find 43. But he's going to not find it. And how is it happening? So T1 searches for 43. He starts by looking at the first key, sees it's 7, too low, you have to go on, so it looks at next, finds this is 15. He has to look at the next pointer, but before he does that, there's the other guy who comes to delete 15. This guy, disconnects 15, and now he uses it he reclaims this space and uses it to reallocate. So he's doing now insert of 80. He takes this space and uses it for 80. So now he puts 80 here. He connects it properly. Now all the keys are sorted. But now the first guy wakes up and looks for the next key. So he's here because it was 15 once. Now he looks for the next key. The next key says there's nothing more in the list. So basically, this guy, T1, deduces that there is no 43 in the list, right? And saying that 43 is not in the list, we use a correctness criteria called linearizability, but whatever you adopt as your correctness criteria, this cannot be the answer. 43 was always there. You cannot return and say it's not there. So that's an error. So we have to do something about it. We cannot just assume that everything works well in a concurrent setting. So the main problem is that T1 used data that was in a memory space that was reclaimed, reallocated, and is now not what he expected to see. So you cannot use data from somewhere that was reclaimed. And also there is another problem called the ABA problem. I'm not going to talk about it for lack of time, but you have more problems than what I've described. You really have to do something in order to get correctness in a situation like that. Okay, so the first thing they did 25 years ago was to say, let's separate the two tasks. I have this concurrent data structure that has to synchronize, has to do everything correctly and efficiently. Let's do that separately. And then let's talk about how to reclaim space, reclaim memory space whenever it's disconnected from the data structure. And the way to connect between them is that the program disconnects a node. Now it's not available for the data structure anymore. And then it says, I'm going to retire this node, right? This node has been disconnected. And the safe memory reclamation component is now responsible to decide when that space can be reallocated for another node. This is the responsibility of this, and this is going to be the topic of our discussion. Okay, separately from all the synchronization that you need to do the data structure correctly and so forth. So how do you decide when to reclaim space? So the traditional schemes, like if you go 25 years ago, one is epoch-based, it's very simple, by Harris. There's hazard pointers that got the Dijkstra Award. And there's reference counting, which I'm not going to talk about. In the initial paper, they had to change the hardware for it to work. Today, there is more work. Hao and Guy did some work on combining hazard pointers and reference counting. that is competitive with what we have today, but I'm not going to further talk about it. But epoch-based is the simplest thing. What you do is the safe memory reclamation. So it gets a node that was retired. Now it knows that it's disconnected from the data structure. To make sure that no one is looking at it, just wait for all the threads to finish, to complete an operation. If all threads are starting new operations, it means that none of them can see this because it's disconnected. If you start a new operation, you will never see a node that was disconnected from the data structure. So this is the epoch-based scheme. And it's very simple. The problem with it is that it's blocking. If you wait for all the threads to finish an operation, if a thread is not completing an operation, you're stuck. You cannot reclaim, you cannot allocate, you're stuck. So there could be occasions where you're blocked and you cannot do anything. So this is a problem if you want some guarantee that everything will work eventually. The second method, I want to talk a little bit more. So this is hazard pointers. What happens here is that the program threads are saying, I do not want you to reclaim this or that object. Okay, so each thread has several slots for hazard pointers, and it writes the objects that it doesn't want the memory reclamation to reclaim. So that's fine, and it works very easy as you think. If I want to delete, I disconnect the node and then I retire it. The reclaimer just gets all the retired nodes. It checks which of them are protected by hazard pointers. Whatever is not protected by hazard pointers can be reclaimed, reused, everything is good. The real problem is when I access a node and I want to protect it. What happens there? Now, so suppose I'm currently on 15 and I want to move on to 20. So I first read the address of 20. So I get the address of what I want to go to. Then I protect it. I install a hazard pointer saying, please do not reclaim 20. I'm going to look at it. But then between these two, maybe someone reclaimed it because I had this address but not yet protected it. So there's a danger here of a race. And so after I protect it, I have to check that it was not yet reclaimed. Only then I can go on working with it. So, and this is a bit problematic. So there are several problems with it. First, it's costly to install a hazard pointer. You have to, so I'm going over a linked list, and each node that I want to read, I have to write a hazard pointer, and I need this hazard pointer to be viewed by all the threads. And this requires a memory fence. If you're doing systems, you know that memory fences are very expensive. I need my write to reach all the other cores in the system. So this is costly. And then if you have a code and you want to verify that this is still alive, if you don't really know the code of the data structure, how do you know if the guy was reclaimed or not? If you know the data structure very well, you'll be able to check if it has been reclaimed. But if you don't know the code, it's really hard to put this reclamation system into a data structure that you're not an expert in. And finally, if it has been reclaimed, now what do? You have to somehow get out of this situation. You were supposed to go with this code. Suddenly it tells you, oh, you're now touching a node that was reclaimed. You have to do something again. You have to go back somewhere. And all of this, when practical people do it, they say, oh, it will be OK. Look at the code, and it will be OK. For theoretical people, it's really difficult to say what you do in these cases. You have to have a code that's structured in a specific way that guarantees that there's a way to go back in the code and you don't make problems in the memory that will interfere with someone else's execution. And so all these problems, and in addition, it's not applicable to all the data structures. So there are data structures where you cannot use it with. And there was a paper that checked 24 data structures and found that 18 were not possible to use with hazard pointers. Now, that paper might have been biased because he wanted to make a point, but still there are lots of data structures that you cannot use with this method. So So it's not the best, right? The previous one, so you have this problem that epoch-based may bring unbounded space overhead, and this is inefficient. It's not applicable to everything. It's not easy to integrate. Both of them are not so good. So we're in a situation that's not so good. And then for about 10 years, there was nothing. And then there was a first paper that tried to improve hazard pointers. This was by us. It was, I will not talk about it. The result is really minor. But it was the first attempt to make a change in this. And after that, there was a flood, right? There was another one in 14, 4 papers in 15. And by now, there's a huge number of papers that try to improve over these two methods. I do want to talk about one of them. This is, as I said, the optimistic access, because it's not improving over these two methods. It's going in a different manner. So I want to shortly explain what it does. So this is Nachshon Cohen, and the attempt is to work optimistically. Optimism works in many areas in computer science. Let's do it here. So the optimistic access says, the memory reclamation can reclaim everything. I'm not that careful and conservative as I was previously with all these methods. I just reclaim everything. Anything that's retired, I can reclaim. Now it's the obligation of the program. It's the responsibility of the program to make sure it doesn't use anything that was reclaimed. So the program, if it reads reclaimed objects, it restarts. And it has to go somewhere back in the code. And it knows that it cannot proceed with the values that it read. So it turned out to be very fast, very low space overhead. And it's nice because it has never been tried for memory management. I'm also talking about, you know, if you go for garbage collection for Java and things more high level, there was never optimistic methods tried then. So it's kind of first time this was tried. Nachshon focused on the reads. Of course, if you write by error optimistically to something that has been reclaimed and reallocated, this can cause damage. So he said, I'm doing it only for reads, which is a disadvantage. And he used hazard pointers to protect the writes. But I want to say that reads are the most important, because if you think, for example, of a skip list, you have log n reads until you get to a point where you want to do a modification, and then expected number of modification is 2, right? And in a tree also, you do lots of reading until you do an update. So, and of course, if you just look for a key, then you only read. You only do reads. So there's a lot more reads in a program than writes. And so the fact that he solved reads was very good, and he got this very good behavior. So I will not go into the technique how you identify if you actually read something that was reclaimed. You have to read the paper. I'm just going to say that if you compare, so this is a hash table, so if you compare epoch-based hazard pointers and optimistic access, the higher is better, and the highest line is when you do no reclamation at all. So you don't do too many operations to get out of memory, but you see that optimistic access is almost like not having any overhead. The same for a skip list. So the pros are that it's efficient and there's minor memory footprint. The cons is it's not easy to integrate. If you fail, you read something and it has been reclaimed, you have to somehow go back, which is, like the previous schemes, is not easy to integrate with the data structure. You have to know the data structure to understand where to go back. It's optimistic only for reads. It would be nice to have also writes. And you cannot return space to the operating system, because if you try to read something that has been returned to the operating system, you may get a segmentation fault if this is not your process anymore. So like subsequent work, so this is the work with Gali Sheffi and Morris. Solve the problem for writes. So it makes sure that if you write to a reclaimed object, it fails. You will never write to a reclaimed object. And there was also work by Portuguese guys, Moreno and Roca, which was published in SPA, where they show how you can return space to the operating system. This was a really nice systems paper with some cool tricks. I will not talk about these subsequent works. So this is the optimistic access. And there were like all these papers, and none of them got it right. So, and then I want to get to the last one, where Gali said, let's show that you cannot get all the things that you want. Let's show it formally. And so it turns out that what you have to do in order to do this, it is not hard at all. It's not complicated. All you have to do is define things properly, and then it all falls into place. It's really, really nice. So what do you want from a reclamation scheme? So of course you want it to be efficient and simple, but this is not something I can define. I mean, it's not like it's computational complexity. You have to actually evaluate it to see which one does better. But what you want is you want bounded space overhead. That's called robustness. So if things are retired, you want to be able to allocate them, to reallocate them. They shouldn't just stay in the retired list without being able to use them. So you want bounded space overhead. You want ease of integration. So you want to easily integrate it even if you don't exactly know what the data structure is doing and you're not an expert on the actual algorithm. There has to be an easy way to integrate it. If you think of epoch-based reclamation, it is really very easy. You announce when you start an operation and when you finish an operation, and that's enough. So there are schemes that are easy to integrate, and that's something that people want. It's really useful. It has to be applicable to most data structures, at least to the data structures that you want to use, right? It has to be applicable, otherwise it's not useful. So can you get all of this? And the answer is no. And it's not very complicated to show it. So this is the Erez theorem, right? This is, you cannot have ease of integration, robustness, and applicability simultaneously in a memory reclamation scheme. You can have two of these, but you cannot have all three. So this is interesting. So you have to define it all. How do you find a proper, adequate memory reclamation scheme? So either all the accesses touch unreclaimed memory, and then you find this is the conservative way, and this is the way it was always. You want to also allow optimistic reclamation. I mean, here I'm waving hand, but in the paper you have full definitions accurately if you want to check. So if you want to also allow optimism, then you're saying, if I read something that has been reclaimed, I do not use the obtained value. If I write something to something that has been reclaimed, I must fail. I cannot write to something that has been reallocated. And finally, I have to access program space. Otherwise, I'll have a fragmentation, a segmentation fault, and I will crash. OK, so this is easy. This is what you want. And then there's three properties that we have to define. First, robustness. So I want to be, there is to be bound on the number of nodes that I've retired, but I cannot reallocate. So this bound has to be, you can say a constant, or you want it to be sublinear, polynomial, exponential if you want, but there has to be a bound. And when I say sublinear, it's in the live data. So if you have a data structure that has n elements, maybe I don't want you to put on the side more than n square elements. Okay? I want some bound on how many elements you reserve in order for your reclamation to work correctly. So I want this to be bounded. And also, so for ease of integration, I want two things. I want that the memory reclamation scheme will not change fields that the data structure is changing. I mean, no memory reclamation even thinks of doing that. I haven't seen anyone even try to do this, but I want to say it formally. You cannot change things that the data structure is using. It will be really difficult to do that without understanding what the data structure is doing. And the second thing is what we had in all these memory reclamation schemes is that you fail some test and then you have to go back and try again. And there it requires understanding of the data structure. So if it's easy to integrate, you have no rollbacks like that. These are the two requirements that we make. And finally, I want wide applicability. I prefer it to work for all data structures, but if you want, there are all kinds of variants that you can do. Maybe access-aware implementation. These are a few data structures that were defined somewhere. You have normalized data structures. And of course, I wanted to maintain correctness. It goes without saying. I put my memory reclamation scheme. It doesn't break correctness. And I wanted to keep the progress guarantees. So maybe if you were lock-free, you will remain lock-free, and progress guarantees. So these are the three things that you have to define exactly in order to do the proof. But now, hopefully, yeah, I will do the proof, and it will be really easy. You will see it's amazingly easy, actually. OK.
So
yeah.
The first bullet, the bound is not in the number of concurrent processes at all? It's not a function of that at all?
I mean, you can take that as, OK, the number of processes have to be bounded. If you have data structure of size n, and I'm allowing you n square bound, how many processes? If you want more than n square processes?
It's sublinear, right? Does it need to be sublinear?
I will prove it even if you take exponential, my proof will work. So I'm really, take all these definitions in a very liberal manner, and you cannot do this. It's amazing, and you'll see the proof. It's very easy. Okay, so so this is the name of the theorem. Comes from easy integration, robustness, and wide applicability. And let's do the proof sketch. So first of all, if it's easy integration, I have no retries and no data structures fields that are changed by the memory reclamation. If I want robustness, I want an actual bound. So I'm telling you that throughout this execution that I'm going to build, there will be 1 or 2 nodes in the data structure. Now choose your bound as you like it, 2 to the n times 100 or whatever you want. Give me a number that's, if I accumulate this number of nodes, one of them will have to be reclaimed. Say it's 100, okay? For 2 nodes in the data structure, if I go over 100 retired nodes, one of them will be reclaimed. You can put 1,000 here if you like, or 1,000,000, whatever you like, put here, and I will work with it. Okay, and then it has to be widely applicable, so let's say just Harris's linked list. I could use various other data structure, but it will be the easiest for me. Take Harris's linked list. It has to apply to it. I'm going to use this as my algorithm in the execution. So here is the beginning. I have 2 elements in my list. And now there is T1 comes, and he wants to check if 43 is in the list. OK? He has to check it. And then T2 comes and start modifying the list. So he's going to insert 3. And so first he's deleting 1. So I'll never have more than 2 nodes in the data structure. Deleting 1 first, and then inserting 3. OK? And then deleting 2 and inserting 4, and so forth. If you just, I'll skip all these things, and eventually I have just 1 element in the list. Throughout, I will have only 1 or 2 elements. And this is how it looks. This is how I want it. This guy has to walk through 100 retired nodes. At this point, because of the bound you said you were going to keep, one of these 100 retired nodes has to be reallocated. That's guaranteed because of the bound. So what happens now, suppose 3 is the bound. What happens now is the T1 starts to look for 43. He's going to walk on until he gets to this node, and then he has to read it and use it, because that's what Harris's list says. You go on, and you go through it. And this is an error. You cannot have him touch and use something that has been reclaimed and may be reallocated. So I just built this contradicting run just for a single data structure. If you only promised me that it will be easy integration and robust. So, so you want wide applicability, just do it for 1 data structure. And I could do lots of data structures with the same example. So you can think maybe here I may change, maybe the memory reclamation scheme will change this so I don't get here, but it's not allowed to change fields of the data structure. So this cannot be saved. And also maybe it will tell it to go back, but you're not allowed to retry. You cannot go back. You have to keep it as Harris's linked list, and this means you have to read this, so you cannot avoid this error. And that's it. That's all showing that, I mean, okay, doing it formally takes more, and there is, it's all in the paper, but this is it. So you cannot do all three simultaneously. And this is really bad news. So, and the proof, if you see, it's not hard. It's very general. I mean, very weak robustness. Just give me a number for 2 nodes, and this will be enough. Very weak applicability. I just took one data structure. If you want wide applicability, it has to work with many data structures. Are the properties important? Of course, robustness. It's necessary to have guarantee of progress, because if all your memory is not reclaimed and just waits there in the retired list, then you're dead. Easy integration, it's needed for practicality and for bug avoidance. And wide applicability, you just want things to work with your data structure. So you need all of this, and you cannot get that. And I want to say this is something that really interests people in the real world. Just in June, I've been in PLDI. There have been 3 papers on these, on memory reclamations for concurrent data structures. And you had previously in PIPO, PLDI, and SPA. So there are lots of work going on. You cannot have the last paper, but maybe, with understanding of this limitation of the impossibility, you can design something that will work better than what we have today. Okay, and that's it. These are the real pictures, by the way, without ChatGPT. This is Nachshon, Gali, Morris, and Maged in real life. Okay, and that's it. Thank you very much. We made it on time. Yeah.
So I have sort of a question from the time that you got this negative review and you thought about proving a lower bound. Like, did you think you could prove a lower bound, or does it say, oh, that just seems too hard to prove a lower bound? Like, what's the story? How long did you sort of try to prove a lower bound until you thought, oh yeah, we can prove something?
It took some time, but we were confident that it's really difficult to get all of these things together. We had the intuition. You develop an intuition after you work in a field.
Yeah, but intuition to be able to formally prove something or different.
Right. We didn't know if we'll make it, but we had the intuition that this can be proven, and eventually we were able to do it.
Eventually means 6 months, a year?
Yeah, maybe 6 months would be a good. You have to try how to define it and how it will work, but eventually it seems very natural and it works in a very liberal manner. So it was stronger than we thought we'd get.
It was good to have the rejected paper.
Yes.
So it seems like, so with the epoch-based thing, you mentioned that you need to know when an operation starts. That's one answer. You need to know when an operation starts. So isn't that alone enough to do a restart? I mean, why is that not an easy integration?
The SMR is very easy there, because what it does, if it has a retired node, it only waits until everybody finishes an operation. So all it has to do is to check that because it's disconnected from the rest of the data structure. So if everybody completes an operation, then everyone that comes will not see it. Now you can reclaim it. So all you have to do with your interaction with the data structure is the data structure will tell you, I finished an operation. I'm thread 37, I finished an operation. And that is pretty easy to implement for the data structure. So,
but I guess what I'm arguing is that it's easy to also instrument when an operation starts, right? So I guess it seems like there's a class of data, so maybe that's not the wide applicability, but it seems like there'd be a class of data structures where whenever you're in the middle of operation, it's always safe to restart from the very beginning.
The epoch-based is applicable to all data structures. It's
No, I'm talking.
But if you take a data structure and you want to get back somewhere, it's a problem if you already change, like if you passed your linearization point and now you want to go back, how do you do this? You've already influenced the data structure, right? So you have to really analyze it and say, from here I will go back to after this,
I see,
right?
so it's more like a database commit, right? So once.
Yeah, you could think, yeah.
As long as I'm in a situation where I haven't committed any state,
I can go back
I
to
can
the
always
beginning.
jump
But
back.
you have
That's
to be
easy find
careful.
when it starts.
You don't commit, but you also don't ruin anything in the shared memory in any case.
Yeah,
and then you can
but
go
to make
back.
that work, you have to have like, whatever shadow copies of things so that you didn't actually update real state.
You could do that. Usually these things are a lot more efficient. So if you had something like that, you could work easier. If you had something like a commit and a log of things you want to change, then it would be a lot easier. But
So
these
is
things are very fast.
Yeah, so if this whole thing was like in transactional memory, for instance, then you could do it, right? You just
Yes,
go back and.
I could go back very easily. And then I would have less problems because either I make my transaction or the memory manager has managed to take my node. But one of them would fail. It makes things a lot easier. Yeah. Yeah.
I can probably have a follow-up question for that. So the proof is very interesting and is very, as you mentioned, liberal and intuitive. So my question could be, because this proof relies a lot about our assumptions. So I want to know how tight this proof is. Like, what if we allow restart? Or what if we allow the memory allocator to kind of understand something of the data structure, like we understand the compute graph or what? Like, if we take one of these things out, are we still getting this result, or we are getting a
So
different
this result says if you have these three things that you want, you will not get it. If you want
Yeah.
just two, we know how to get it.
Oh, so you mean for any two of them, we know the result, but
Yes.
three, it's impossible.
Right.
I see. So
And you want the three of them.
I
You really
understand.
want them.
I see.
So.
Okay.
All right, and then speaker again.
Morse looks like he's scowling there. Did you?